Yes, compare growth functions. P.2. Yeah. Here, because if recall, we go back to our part A of module 2, we have some uncompleted work. We didn't do the comparisons. We have two methods for the element uniqueness problem. Yeah, so let's recall from part A. Yeah, recall. We have two methods for the problem element uniqueness uniqueness, yeah, problem, yeah, probably this E or not, yeah. Anyway, two methods, but we didn't compare these two methods, right? Yeah, so we will do the comparison here, okay? But when we compare their growth functions. Because we just learned those growth functions. So here, for simplicity, we just compare their growth functions. Yeah. All right, so let's do that. Compare two growth functions for those two methods. Which method is better? Yeah, we want to get an idea here. Okay. For the first method, we use the worst case. CW, the first method, it corresponds to the worst case. Yeah. Worst case expression. And for the second method, yeah, also the worst case expression, n log m plus n minus 1. Yeah. These two are two original functions, not the growth function. Yeah. So we need to extract growth functions from them first. Okay. The growth function of the first method 1, just n squared. Okay. Yeah. And the growth function of the second one, n log m. Yeah. Let us compare these two functions here. Okay. Yeah. We use ratio to compare these two growth functions. Yeah. Just like what we did in the previous slide. Yeah. But here, let us consider the ratio of these two growth functions when n goes to infinity. This time. Yeah. All right. After cancellation, we find the limit when n goes to infinity, n over log n, log function, n function over the log function. Yeah. But the log function, what is the base of this log? Okay. Yeah. So here we can consider the general log base a, but this a, we like to take a greater than 1. Yeah, because only when a greater than 1, this function is positive. Otherwise, it's negative, right? It does not make sense. Yeah, so your growth function is a negative function. It does not make sense, right? Yeah, so we take, the growth function positive. Yeah. Actually, n log n, remember, this n log n comes from sort algorithm. The sort algorithm, the log, we got from there log base 2. Log base 2. So that corresponds to a greater than 1, right? Yeah. So our assumption is right. Okay. All right. And here we want to see this ratio goes to infinity when n approaches to infinity. Yeah. How do you see that? Yes. Let me show you the details. Yeah. We can see that. How do you see that? Yeah, here, let me show you the details. Yeah. The method one, here I use two methods. Yeah. The method one, we do some variable substitution. Yeah, because the log, we feel we cannot see log clearly. Yeah, we want to avoid that log. So we do variable substitution. We introduce a new variable called u. U equals that log function, log base a of n. Okay. Yeah, with this substitution, yeah, n equals a to the u. Yeah. Then our original limit, we switch to new variable u, it becomes a to the u over u. A is an exponential function. Okay, exponential function, we know exponential function with base a greater than 1. Yeah, still we use the base a greater than 1. Exponential function dominates any polynomial, right? Yeah, exponential function dominates the polynomial, so that should be infinity. Yeah, but to see that, yeah, to see that, we can do calculation. Yeah, we can use, calculation to see that. Okay, yeah, yeah. Later I will show you. Yeah, we can use rigorous math to see this fact, this dominance fact. Okay, yeah. Later I will show you. Yeah. All right. Yeah, here we make our conclusion based on this property. An exponential function dominates any polynomial. Yeah. So that is our, everybody knows this fact. Yeah. We can prove it. Yeah. Later I can prove it. Okay. All right. That's method one. Method two, let's recall calculus, L'Hopital's rule. I believe many of you forgot the details of this part in calculus. Actually, it's in Calc 2. Calc 2 course. All right. Yeah, that part. Yeah. Yeah, let me explain that. Yeah. Method number two, we use L'Hopital's rule to calculate the limits here. Yeah. All right. L'Hopital's rule, when we use it, we work on limit of ratio of two functions. Yeah. But many times, if you work on directly, not very easy, pretty hard. But L'Hopital's rule tells us we can convert it to limit of the ratio of two derivatives. Yeah, that's the same. Derivatives will be easier, and then you can calculate the limit in an easier way. So that's the L'Hopital's rule. How the essence of the L'Hopital's rule. Okay, yeah, all right, yeah. But when you apply L'Hopital's rule, there are some conditions. Before you apply it, you need to check some basic conditions. So that is, the ratio should be indeterminate form, not determinate form, indeterminate form. So what's the indeterminate form? Infinity over infinity. So that is the first indeterminate form, because that cannot be determinate, right? Yeah, it could be anything, infinity. So that's the form. Yeah, do not treat as we use that real infinity over real infinity. Do not treat that. Okay. Yeah. So here we look at that as a form, as a form, not as a number. Okay. Yeah. If you treat this expression as a number, it does not make sense. It does not exist. There is no such number that equals infinity over infinity. Okay. So we do not treat it as a number. We treat it as a form. Okay. So that the meaning of that form, it is the ratio of two functions. The numerator function approaches to infinity when n is when n goes to infinity. The denominator function also approaches to infinity when n goes to infinity. That's the meaning of this indeterminate form. Okay, all right. Another possibility is 0 over 0. All right. Still, we treat it as a form, not a number. If you try to understand using the number way, 0 over 0, it does not make sense. Okay. Yeah, it does not exist. There is no such number. Okay. But if we understand it as a form, it makes sense. As a form, it makes sense. Okay. So that means the numerator function approaches to 0 when n approaches to certain number. Similarly for the denominator function. Okay. Yeah. All right. Here, let us consider. Yeah. So now I show you how to calculate that a to the u over u. This is an indeterminate form. Yeah. I use L'Hopital's rule to show you. This one, okay, yeah, it corresponds to infinity over infinity indeterminate form, right? So, yes, after you identify it is an indeterminate form, then we can apply L'Hopital's rule correctly. Otherwise, some students forget to check the indeterminate form. Then, if they still apply L'Hopital's rule, they may get a wrong answer. Okay, wrong answer. Yeah. All right. So now we apply L'Hopital's rule. Let's take the derivative. Yeah. By the derivative formula, the derivative of an exponential function, it equals natural log of a. The base number, we take natural log as the constant, then multiply this exponential function again, a to the u again, and denominator u, its derivative is 1. Its derivative is 1. Okay, yeah, by the power law, right? Power rule. Okay, so u to the n derivative, there is a power rule. Because this is a power function. Okay, power rule, its derivative is n times yeah, n times u to the n minus 1. Okay, yeah. Yeah. Here, so by that power rule, derivative is 1. Okay, yeah. Then we can see when u goes to infinity, yeah. Here, this new ratio, you should not take L'Hopital's rule another time because it's not an indeterminate form. Yeah, the numerator is 1, constant. It does not go to infinity. All right. Yeah, the numerator is a constant. Yeah, so you should not apply L'Hopital's rule. Second time, you will get a wrong answer. All right. Yeah. So we just, because here here we ignore the constant part. Yeah, the ratio 1 is gone. You know, the constant part never changes. So where u goes to infinity, that exponential function goes to infinity. Yeah. So that is the answer we used in the previous slide. Okay. Yeah. So here we do the rigorous math. We can see that. Okay. Yes. All right. But in this simple example, we use that L'Hopital's rule. All right. Calculus. Calc 2. All right. Yeah. Okay. Yeah. Yeah. Definitely we need a greater than 1. Otherwise, yeah, think about if a, yeah, if 0 less than a less than 1, we won't get this infinity. So we will not get that infinity answer. Okay, yeah. So the range for a is also important. A greater than 1, strictly greater than 1. Even 1, it's not good. We have to exclude one case. Yeah. All right. Yeah. Even 1, we cannot. Yeah. All right. Yeah. All right. Yeah. Yes. But here, yeah, there is another issue I may need to, you know, because I mentioned the rigorous math, right? I mentioned that rigorous math. Yeah. Here for the rigorous math, when we apply L'Hopital's rule, we need a continuous variable. Continuous variable. What do you mean continuous variable? Okay, your variable can take values of all real numbers. Yeah. Your variable can choose numbers that can change continuously. Okay, yeah, not discrete variable. Not discrete variable. All right, so how to get that point? Yeah, here, this is another, here regarding the rigorous math. Okay, regarding the rigorous math. All right, so let me make this point here. Yeah, why we need to use the continuous variable here. Yeah. All right. Let's look at this limit of the ratio n over log m when n goes to infinity. Yeah. First, let's look at the values for n. Because we know the meaning of n, the problem size, right? Its original meaning, problem size. And the valid numbers for the problem size, natural numbers, right? 1, 2, 3, and so on. Natural numbers, not arbitrary numbers, right? 1.2, that's not a good problem. It's not a valid problem size. 8.5, that's not the valid problem size number. Right? So here, the two functions, n and the log n, we use the discrete variables here. Discrete. Okay. Discrete variable here. All right. Yeah. Discrete variable here. The discrete variable, then we cannot take a derivatives. Derivatives. Yeah. So here, derivatives require continuous variables. Okay, continuous variables. Yeah. But how to get around that? Yeah. If you do not do anything, you just apply L'Hopital's rule on this discrete version of the ratio function, your work is not rigorous. Okay, your work is not rigorous. Yeah, so we should avoid that. Yeah, because we may get trouble if you do not do your work rigorously. Sooner or later, you may get trouble. You may get some wrong conclusions. So we want to avoid that part. Okay, so we are doing science. It must be rigorous. Our logical reasoning must be rigorous. All right, yeah. Here, but we can get around it. We can solve that problem easily. Okay, all right. So the logic is like this. All right, yeah, discrete variable. All right, the logic is we convert discrete variable to continuous variable first before we do the calculation. Before we apply the L'Hopital's rule, we do conversion from discrete variable to continuous variable. All right, yeah. So how to do that? We consider the continuous version of the ratio. How about that? We consider, now we replace discrete variable n by a continuous variable x over log function of x. But this time, our x, we can take 1.2, 8.5, and so on, right? We can take any positive real number. Yeah. So because our n is not necessarily the same as n, right? So any positive real number is allowed here. Okay. Yeah. There, we have no problem to apply the L'Hopital's rule, right? Yeah. Yeah. All right. So we can take the derivative. The derivative of x equals 1. Okay. The derivative of that log function, we assume the log base is a. Yeah. So that is 1 over bracket natural log of a times x. The derivative formula for the log function. Okay, yeah. After simplification, we take the limit when n approaches infinity. This limit function, natural log of a, the constant, times variable x, when n goes to infinity. It is infinity. Okay, yeah. But this limit, we use the continuous variable. Yeah, goes to infinity. All right. But our original limit, that's on the discrete variable. So the question is, can we come back after we get a conclusion for the continuous variable version of the ratio of the limit? For the limit, can we come back to the discrete version to make a conclusion? The question is yes. Yeah. So we can come back to our discrete variable version and make the conclusion. Its limit is also infinity. Why this kind of conclusion is correct? Yeah, the reason is very simple. The reason, yeah, to explain that, we go back to the definition of limit. Let's recall the definition of limit. Yeah, how do we define limit of a function in our calculus? Here, I do not need to show you the, the complete definition here. Here, I just explain, the basic idea when we define the limit of a function. So here, limit of a function when n approaches to infinity. Do we need to take any specific way for x to go to infinity? How does x approach to infinity? So here's the question. How does x approach to infinity? Because there are so many different ways to approach for x to approach to infinity, right? So many different ways. For example, so here for x approaches to infinity. Here I can take two different ways. The first way, 1, 2, 3, and to infinity. Second, 1 square, 2 square, 3 square, it's another way, n square way to infinity. We have infinitely many different ways to go to infinity, right? You can also, use log 1, log 2, log 3. That's also log of n to infinity, right? There are so many different ways to approach to infinity. But in our limit definition, do we need to specify which way for x to approach to infinity? No, we do not need to specify. No need to specify any way. So any way works, okay? The limit, any way to infinity works. Okay, that's important. So that's from the definition of the, no matter which way you take for x to approach to infinity, the answer is correct. So that's the limit definition. All right. Here we just use that because any way works. Let's take the discrete way. How about that? Here we take the way, one special way, the discrete, so let's say, because discrete could be any discrete values, right? So here let's take the natural number way. Okay, we take the natural number way, all right? After we did a calculation for the continuous variable to get the limit, then we take the special natural number way. It's still correct. Okay, it's still correct. So in this way, we get around the discrete variable problem. We get around it. Okay, and our logical reasoning is completely rigorous here. Okay, no problem, completely rigorous. All right, and here I spend a lot of time to explain that because this non-rigorous way is in our textbook. Okay, in our textbook it used this non-rigorous way. So I want to point it out. Okay, so even if it appears in our textbook, but it's not rigorous. All right, you should avoid it. You should avoid this kind of logical reasoning. non-rigorous logical reasoning. All right. All right. Yeah. So I run out of time. Yeah. So let me stop right here for our part B of module 2.